tech giants are currently wiring just absolute billions of dollars to cloud providers right now to train single AI models.
Yeah, it's staggering.
It really is. Right? It is a scale of capital expenditure that honestly rivals like national infrastructure projects.
Oh, easily.
But if you were to somehow freeze time,
Right.
and just pry open an NVIDIA H100 chip inside one of those massive server farms, and look at what those billions of dollars are actually buying at the microscopic level, you wouldn't find some mystical emergent intelligence.
No, definitely not.
You would find a relentless, incredibly expensive blame game.
Right.
So today we are cracking open the foundational math of that blame game. Welcome to the deep dive.
Glad to be here for this one.
Yeah, we are unpacking a really fascinating, highly detailed architectural breakdown of the first principles of AI compute.
Specifically focusing on the exact mathematical reality that, governs why AI actually costs what it does.
Right, because it is the ultimate demystification exercise, really. We're stepping away from the marketing jargon.
Yeah, the whole sparks of ABI stuff.
Exactly, all that hype. And we're looking at the absolute brutal economics of linear algebra.
It's all just math. And the source material we are working with today isolates the exact variables that dictate the computational workload of large language models.
Which is what they use to build budgets.
Exactly. It breaks it down into a framework that actual hardware engineers use to budget supercomputers.
And at the center of that framework is a single formula. I mean, it's literally just 6 characters long.
Yeah.
But it essentially dictates the financial gravity of the entire tech industry right now. And that formula is 6ND.
Right, 6ND.
If you understand 6ND, you understand exactly how raw data and model parameters turn into intelligence.
And maybe more importantly, you understand the physical bottlenecks that actually limit that process.
Exactly. So I want to bypass the basic definitions today. I mean, you, the listener, we all know these models have hundreds of billions of parameters.
Right, and they chew through trillions of tokens. We know that part.
Yeah, so let's look at how this formula treats those two massive variables.
Yeah.
So we have N for parameters and D for data tokens. The premise of the source is that we can represent the entire computational complexity of a massive neural network purely with those two numbers.
Just N and D.
Right. But looking at the math, I mean, that implies deep learning is essentially 99% matrix multiplication. I have to push back on that immediately.
Okay, let's hear it.
Like, what about all the other stuff in the architecture? You have layer norm, you have activation functions like GLU or SWIGLU.
Right. Positional encodings, all of that.
Yeah. Are we seriously saying that in a multi-billion-dollar budget, those operations are just completely free?
I mean, it is a totally valid point of friction when you first look at the 6ND formula.
Right, because it feels like we're ignoring half the model.
It does. But the short answer is, yes, we treat them as essentially free.
Really? Free?
Yeah, but the why they're free requires us to look at computational complexity classes. Specifically, how different mathematical operations scale when we push a model to the size of, a modern LLM.
Right, the sheer scale of it.
Exactly. It comes down to big O notation and the actual physical hardware architecture.
So the workload scales at, like, radically different rates depending on the type of math we're doing.
Exactly. Let's separate the math into 2 buckets just to make it easy.
Okay, 2 buckets.
In bucket 1, you have the massive matrix multiplications. These happen in the linear layers, which is where your n parameters physically reside.
Right, the actual weights.
Right. The mathematical scaling of a matrix multiplication is O of ND. So the computational cost is simply the parameters multiplied by the data.
Okay, makes sense. What's in the second bucket?
In bucket 2, you have the element-wise operations you just mentioned.
The activation functions and normalizations.
Exactly. These don't scale by the total parameter count. They scale by O of D times H.
Wait, what is H?
The H is the hidden dimension of that specific layer.
Ah, okay. So the hidden dimension is just the width of the data vector as it moves through that one specific layer.
Right.
Not the total volume of weights in the entire model.
Exactly. And here is where the physical reality of the hardware makes those element-wise operations just, vanish from the accounting sheet.
Because of the size difference.
Yes. In a massive modern model, your hidden dimension, that H variable, might be 8,000 or maybe 16,000.
Okay.
But your total parameter count, your N, is, say, 70 billion.
Oh, wow. Okay, yeah, that is a massive gap.
Right.
So the matrix multiplication is scaling against a number in the tens of billions, while the activation function is only scaling against a number in the low thousands.
Exactly. The operations tied to the hidden dimension become a mathematical rounding error.
It's just totally eclipsed.
Right. If you are an engineer tracking FLOP's floating point operations, the matrix math is consuming like 99.9% of the GPU's time. The non-matrix operations are processed so quickly by comparison that they simply do not move the needle on a $1 million cloud invoice.
So they don't even bother billing you for it, basically.
Yeah, that is why the entire industry condenses the incredibly complex architecture of a transformer model down to just the relationship between N and D.
Okay, that actually makes the math surprisingly clean.
It really does.
If matrix math is the only thing moving the financial needle, let's look at the very first mechanical action a model takes.
The forward pass.
Right, the forward pass. This is the act of making a prediction. I give the model a prompt, the data flows through the layers, and it spits out an answer. And according to the source, the computational cost of this forward pass is exactly 2ND.
Right, 2ND.
2 times the parameters times the data. Let's ground this in the hardware, though. Why the constant of 2? Like, where does the 2 come from?
Well, the 2 comes directly from the physical silicon of the processing cores inside the GPU.
Really, the physical chip itself.
Yes, we have to zoom all the way down to the interaction between a single parameter and a single piece of data.
Okay, zoom in.
The fundamental equation of a linear layer is y equals x times w. The input signal x is multiplied by the weight parameter w.
Right, simple multiplication.
But the hardware doesn't just multiply, it has to combine that result with all the other signals.
Because a neuron in a dense layer is connected to, like, thousands of inputs.
Exactly.
It has to aggregate all of them to fire properly.
Precisely. So for every single parameter in the model, the processing core executes a very specific two-step maneuver.
Okay, what's step 1?
First, it multiplies the input value by the parameter weight.
Hmm?
Second, it adds that newly calculated product to a running total. An accumulator.
Multiply, then add.
Multiply, then add.
And in hardware engineering, that specific combination is baked into the chip design itself, right?
Yes, it is called a MAC, a multiply-accumulate operation.
MLSE.
Modern tensor cores are physically wired to execute one MAC in a single hardware clock cycle.
So it does both steps at once.
Right. But when we audit the total compute budget, we don't count MVIS, we count FLOPs.
Right, floating point operation.
Exactly. A floating point operation is a single mathematical step. Since a MAC contains one multiplication and one addition.
That's 2 steps.
Exactly. One MSE equals exactly 2 FLOPs.
So if you have n parameters in your model and you need to process them, that requires 2n FLOPs. And because you are feeding the model a data set of D tokens, you have to execute that 2n sequence D separate times.
Right.
Resulting in an unavoidable physical cost of exactly 2ND FLOPs.
That is the physical reality of the forward pass.
Okay, I want to make sure the mechanics of this are absolutely vivid for you listening without getting, bogged down in reading arrays or dry textbook equations.
Good idea.
Let's use a physical analogy instead of the micro example in the text.
Okay, let's hear it.
Imagine we have a microscopic, primitive AI model that consists of just 2 physical volume knobs on a soundboard.
2 knobs. I like this. It visualizes the linear algebra physically.
Exactly. Those knobs are our parameters are in. So n equals 2.
Got it.
And we are feeding it a single audio track, which is our data token, our D. So D equals 1.
Okay, N is 2, D is 1.
The audio track splits into 2 separate signals, one going into each knob. To get our final output volume, the hardware has to look at the first signal, multiply it by the setting of the first knob, and hold that number.
That's the first multiply.
Then it looks at the second signal, multiplies it by the setting of the second knob, and adds it to the first number.
And if we count the actions taken there, you did 1 multiplication for knob A,
Right.
1 multiplication for knob B, and then the additions to combine them.
Yep.
You engaged with each parameter exactly once to execute the math.
Which perfectly aligns with the formula. 2 times 2 parameters times 1 audio track equals 4 total FLOPs.
The math scales perfectly with the parameter count.
It's beautiful, really. So, making a prediction, the forward pass costs 2ND. That is a solid, undeniable baseline.
It is.
But this brings us to the central friction of this entire breakdown. If inference just asking the model a question costs 2ND, why does the source material state that training the model costs a massive 6ND? Where is the hidden 4ND coming from?
Oh, that missing 4D is the exorbitant cost of learning.
The learning phase.
Yeah, it is the backpropagation phase, and this is where we see the sheer brute force inefficiency of how we currently train artificial intelligence.
It's efficiency.
Well, making a guess is cheap. Figuring out why you guessed wrong and fixing the internal circuitry is incredibly expensive.
Let's trace that cost then. The model does its 2D forward pass, and it outputs a prediction.
Right.
But during training, there is a mechanism waiting at the very end of the network, the loss function.
The boss.
Right, the boss. The loss function acts as a highly critical supervisor.
Very critical.
It compares the model's output to the actual correct answer in the training data. It measures the delta, the error, and then it forces the model to work backward to correct the mistake.
And this backward journey is computationally segmented into two very distinct, highly intensive tasks.
Okay, 2 tasks.
Each of these tasks is going to cost us an additional 2 ND, which gets us to our final 6 ND total.
Okay. That's where the math adds up.
Let's break down task A first. This is the calculation of the weight gradient. In calculus, this is the partial derivative of the loss with respect to the weights.
Okay, translating that out of calculus into mechanics for a second.
You do.
Task A is figuring out how much to manually turn those internal volume knobs so the model doesn't make the same mistake next time.
Exactly.
We have the final error, but we need to know where parameter number 40 billion should be adjusted up by a fraction of a percent or down.
Right. We need an update instruction for every single parameter.
Mm-hmm.
And mathematically, to find out how much a specific weight contributed to the final error, you have to multiply the incoming input signal for that weight by the final error.
Back to the soundboard analogy then.
Let's do it.
If the final output was way too loud, and we want to know how much to blame knob A, we have to look at the raw audio signal that was flowing into knob A at the exact moment the error occurred.
Right.
And multiply that by the error itself.
And because you have to calculate this unique blame for every single knob, you are once again doing a massive multiplication sequence across the entire parameter count N.
For every single piece of data D.
Exactly.
Which means we're doing another MAC operation for every parameter. One multiply, one accumulate.
Right.
Another 2ND FLOPs.
Precisely. So we have spent 2ND to make the guess,
Yep.
and 2ND to calculate the adjustments for our own parameters. We are at 4ND.
Yeah.
But the process is only half finished. Backpropagation has a task B.
Task B.
We don't just calculate the weight gradient. The GPU must also calculate the activation gradient.
This is the partial derivative of the loss with respect to the input data.
Yes.
And this is where I really stumbled the first time I looked at the calculus of neural networks.
Oh, a lot of people do.
Like, task A makes perfect sense. We need to change the weights to make the model smarter.
Right.
But task B is calculating the gradient of the data itself. We aren't changing the input data.
No, we are not.
We can't alter the user's prompt or the text in the training corpus.
Yeah.
So why on earth are we burning millions of dollars of compute calculating a derivative for something we are never going to update?
This is arguably the most profound insight in the entire architecture of deep learning.
Really?
Yes, you are correct. We do not update the data. The calculation of the activation gradient serves absolutely zero purpose for the specific layer currently doing the math.
So it's useless locally?
Locally, yes. It is calculated entirely for the survival of the rest of the network.
Okay.
The source material uses a brilliant conceptual model here, the factory assembly line.
Oh, let's walk the factory floor. I like this.
Okay.
We have a deep neural network, which we can visualize as an assembly line with 3 workers. Let's call them worker A, worker B, and worker C.
Got it.
Worker A processes the raw materials, hands the component to B. Worker B does their specific task, hands it to C. Worker C adds the final touches and hands the finished product to the boss, which is the loss function.
And the boss inspects the final product and declares it defective. Let's say it's misaligned by 10 degrees.
Ouch. So worker C, being the one standing right in front of the boss, immediately checks their own station.
Right.
They look at their tools, figure out their own calibration is off, and they adjust their wrenches. That is task A, the weight gradient. Worker C just spent 2ND FLOPs fixing their own equipment.
Exactly. But if the process stops there, the factory is fundamentally broken.
Wow.
Because what if worker C's tools were perfectly fine and the component was already misaligned when worker B handed it over?
Right.
Worker C fixing their own tools doesn't solve the root problem. Worker C must physically turn around, look at worker B, and communicate.
They have to pass the message.
Exactly. They have to say, the specific part you handed me was off by 10 degrees.
And that localized message, that translated error signal passed backward, That is the activation gradient.
Exactly. If worker C refuses to calculate that message and pass it backward, worker B is completely blind to the final error.
They wouldn't even know they messed up.
Right. Worker B has no idea they need to adjust their own tools, and worker A is even further in the dark.
The chain of learning just severs completely.
Precisely. The only way a deep network can learn is if every layer acts as a translator, taking the error from the layer ahead of it and translating it into a localized error for the layer behind it.
So it literally is a cascading blame game.
It really is.
Every layer has to figure out exactly how much of the final failure was their fault, fix their own tools, and then package up the remaining blame and hurl it at the layer behind them.
The source material categorizes this compute in a very elegant way. Calculating the weight gradient, fixing your own tools, is called selfish compute.
Selfish compute. I like that.
You are taking responsibility and optimizing your own local performance.
While calculating the activation gradient is selfless compute, or passing the buck.
Right, selfless.
You are burning massive amounts of electricity occupying the GPU cores, not to improve your own parameters, but simply to package the error signal so the previous layer has something to learn from.
And the mathematical engine driving this entire assembly line is the chain rule of calculus.
Oh, the chain rule.
Yeah. The activation gradient calculated by worker C literally becomes the incoming error signal for worker B.
It's a handoff.
Exactly. Worker B receives it, uses it to run their own selfish compute to fix their weights, and then runs their own selfless compute to create a new activation gradient to pass to worker A.
It just cascades backward all the way to the input layer.
Yes.
This mechanism completely recontextualizes the 6ND formula for me. Like, 4ND, a full 2/3 of the energy and money spent on AI, is just the cost of this internal communication and self-correction.
It's massive overhead.
And it highlights a really practical reality of deploying these models. If I log onto a cloud service right now and query an open source model, I am only paying for 2ND.
Correct. Because during inference, there is no loss function.
There is no boss yelling about an error.
Exactly. The model just blindly guesses. It does the forward pass, the workers hand the component down the line, and whatever comes out the end is the final product.
No one checks their tools. No one passes blame backward.
None of it. You bypass the entire 4ND backpropagation cost.
That's incredible.
And there is another edge case the source points out, actually.
Oh.
If you are only training the very first layer of a neural network, which is rare, but it happens in certain transfer learning setups, you also save 2ND.
Why is that?
Because worker A is at the start of the line. There is no one behind them to pass the blame to.
Oh, right. The buck stops there.
Exactly. They do the selfish compute to fix their own tools, and then they stop. But for a modern large language model with, say, 96 massive layers, 95 of them rely entirely on the selfless compute of the layer above them just to function.
The philosophy of the gradients is fascinating, honestly. But here is where I see a massive physical contradiction.
Okay, let's look at it.
If we look at the core equation, y equals x times w, the math treats the input data, x, and the weights, w, as perfect symmetrical twins. They are just two matrices being multiplied together.
Right. Algebraically, they look the same.
But when you map that math onto the physical architecture of a neural network, their roles couldn't be more different. One is static, the other is dynamic.
Oh, absolutely. The asymmetry between the math and the physical topology is a massive hurdle in hardware design.
It has to be.
The source provides a fantastic mental model to illustrate this physical difference, actually. The road versus the room.
Okay, let's build that out.
Yeah.
Imagine the entire neural network as a long, continuous hallway lined with sealed rooms.
I can picture it. The weights, the W parameters, are heavy, complex machines bolted to the floor inside each of those sealed rooms.
They don't move.
Right. They are completely stationary. They store the embedded knowledge of the AI, but they are entirely local. A parameter living in layer 10 never unbolts itself and visits layer 12.
So when the backpropagation wave hits layer 10 and the weight gradient is calculated, that update information stays completely localized.
Exactly. It is applied directly to the machine inside that specific room.
Right. But the activations, the X values, are the opposite.
Yeah.
They're the actual hallway. They're the road connecting the rooms. The data is a messenger that enters the front door, walks into room 1, gets processed by the machine, steps back out into the hallway as a slightly altered messenger, walks to room 2, and so on.
So consider the logistics when the boss at the end of the hallway detects an error.
Okay.
To tell the machine in room 1 that its calibration is off, the error signal cannot travel through the lock rooms. The parameters can't talk to each other directly.
They're bolted down.
Right. The error must travel backward down the hallway. It has to flow in reverse along the exact activation pathways it used during the forward pass.
The math treats X and W as equals, but the physical architecture treats one as a locked vault and the other as a messenger running a relay race.
That's a great way to put it.
Calculating the W derivative is the act of repairing the machine inside the vault. Calculating the X derivative is the act of writing a complex fax, handing it to the messenger, and sending them sprinting backward down the hallway to the previous room.
It is a fundamental divergence in physical identity. One is a structural update, one is a transit mechanism.
And yet, despite this massive difference in physical reality, the formula dictates that they both cost exactly 2 ND FLOPs to calculate.
Right.
Repairing the machine costs 2 ND. Writing the fax costs 2 ND. Which brings me to a major sticking point I've always had when budgeting compute.
Oh, what's the sticking point?
I want to challenge the premise that the weight gradient is only 2 ND.
Okay, let's hear the friction.
The 2 ND formula accounts for finding the gradient.
Right.
Multiplying the input by the error. But once you have the gradient, you still have to physically change the parameter.
Right.
The mathematical step for updating a weight is taking the old weight and subtracting the gradient multiplied by the learning rate. So W new equals W old minus the learning rate times the gradient. That is a concrete mathematical operation. That requires the GPU to do work.
It absolutely does.
But calculating the activation gradient, writing the fax, doesn't have an update step. You just calculate the error signal and pass it along.
You just send it.
You never actually alter the input data X. So shouldn't the weight gradient calculation be more expensive?
I see where you're going.
Shouldn't it be 2 ND plus the computational cost of the update step? Why is the update step completely ignored in the 6 ND God formula?
This is a highly acute observation, and it's the exact point where theoretical math has to bow to the sheer scale of modern computing.
Scale is the culprit.
Always. You are entirely correct that the update step exists and requires compute. But to understand why it is omitted from the 6ND formula, we have to look at the staggering difference in scale between an O of ND matrix operation and an O of N linear operation.
Okay.
We have to debunk what we call the parameter update myth.
Walk me through the numbers. Why is the update invisible?
Think about that final subtraction step. W new equals W old minus gradient. You have N parameters in the layer.
Right.
You perform this subtraction exactly once for each parameter at the very end of processing a batch of data. So the computational complexity is exactly N operations.
Right. And N is massive. We're talking about 70 billion parameters for a big model. 70 billion operations isn't nothing.
It sounds massive until you compare it to the gradient calculation itself.
The finding of the gradient.
Exactly. To find the gradient that you are subtracting, the GPU had to cross-reference every single one of those parameters against every single token in the data batch. The gradient calculation scales at N times D. Let's use real-world scale. You have a 70 billion parameter model.
Okay.
And let's say your current batch of training data contains 4,000 tokens.
Okay, so to calculate the gradient, I have to multiply 70 billion by 4,000, which is 280 trillion operations.
Exactly. 280 trillion operations just to figure out the gradient matrix.
Wow.
And then you do the final update step, which is just the N parameters. 70 billion operations.
Oh. I see the cliff now. 280 trillion versus 70 billion?
Exactly. The update step is physically 4,000 times smaller than the matrix multiplication required to find the numbers in the first place.
It's nothing.
In the architecture of a massive GPU cluster, that final O of N update step is processed so fast it's functionally instantaneous.
It's a literal rounding error.
It is a rounding error buried in the noise of the memory bandwidth. So when financial architects build their cost projection models, they completely sever the O of N operations from the equation.
They just don't care.
They only budget for the massive O of ND matrix multiplications.
That makes absolute sense. The update is just swallowed by the scale of the matrix.
Right.
But that still leaves the activation gradient. Why does packaging up the error and sending the fax also require a massive O of ND matrix multiplication that takes exactly 2 ND FLOPs?
This is where we hit the most beautiful symmetry in the linear algebra of neural networks.
Oh, I love mathematical symmetry.
It's great. And the source material explicitly highlights this. It calls it the dual nature of N.
The dual nature.
The reason both gradients cost exactly 2 ND is because the variable N means something completely different depending on which direction you are looking at the network.
Wait, I need to unpack that. How can a single variable, like the parameter count, mean two different things simultaneously?
Let's isolate the weight gradients first. When we calculate how to update the locked machines, we are operating with a time or batch focus.
Time focus.
In this context, n represents the breadth of parameters. You have n specific physical dials that need to be adjusted.
Right? I have 70 billion distinct knobs.
But to figure out how to adjust dial number 1, you cannot just look at its performance on a single token of data.
Why not?
Well, if the token is the word apple, maybe the dial was perfectly calibrated, but on the next token, orchestra, it failed completely.
So you need the aggregate performance. You have to average the error out over the whole batch.
Exactly. So for each of the n individual parameters, the GPU must multiply and accumulate its specific error across all D tokens in the current batch.
Okay.
The calculation sums over time over the batch of data. You are multiplying n distinct dials across D sequential tokens. Multiply and accumulate gives you the MAC. The cost is 2ND.
Okay, so for weight gradients, n is the physical breadth of the dials, and we test them across the dimension of time, the sequence of the data.
Right.
How does the activation gradient shift that?
For the activation gradients, we abandon time and shift to a space or depth focus.
It's a base focus.
In this context, n no longer represents individual dials to be tuned. Instead, n represents the density of connections. Look at it from the perspective of a single token of data, a single messenger running backward down the hallway.
We only have D tokens.
Right. But to figure out the exact amount of blame to assign to a single token's activation pathway, you have to trace its impact across the entire physical structure of the layer.
Because in a dense neural network, every input is connected to every single output.
Exactly. That one token didn't just interact with one parameter. When it entered the room, its signal was split and fed into every single one of the 70 billion machines.
Oh, right. So to figure out the true blame for that one token, the GPU has to cross-reference the error signal against all n-parameter connections it touched.
Precisely. So, for each of the D individual tokens, the GPU must multiply and accumulate the error across all n spatial connections.
Wow.
The calculation sums over space over the density of the network's wiring. You are multiplying D distinct tokens across n physical connections. The cost is, unavoidably, 2ND.
That is genuinely profound when you visualize the architecture. One mathematical operation sums over time, averaging the data batches, and the other sums over space tracing the physical density of the connections.
It's perfectly balanced.
And because the architecture of a transformer uses dense, fully connected layers where every input inherently touches every weight, the calculus inevitably collapses into the exact same 2ND computational load in both directions.
It's an inescapable consequence of building a dense matrix.
It really is.
And this theoretical symmetry isn't just an elegant mathematical curiosity. This is exactly what hardware engineers at NVIDIA, Google, and Meta are fighting against every single day.
Right, because theory has to meet practice.
Exactly. The 6ND math dictates exactly how a silicon chip must behave,
Right.
which forces us to look at the engineering reality. We need to look at how this theoretical math hits the physical metal of a GPU.
Okay.
We need to map 6ND onto the roofline model.
Okay. Let's transition from the mass to the metal.
Yeah.
If you are an engineer optimizing a model, the roofline model is your ultimate diagnostic graph, right?
Yes, the ultimate.
It visually represents whether your millions of dollars of hardware are actually doing useful work or if they're just burning electricity waiting for data. Let's build this graph for everyone listening. What are the axes?
The roofline model exposes the deepest bottleneck in modern computer science, which is the memory wall.
The memory wall.
The x-axis of the graph represents arithmetic intensity. This is measured in a very specific metric, FLOPs per byte.
FLOPs per byte. So how much math you can squeeze out of a specific chunk of data.
Exactly. Inside a GPU, the processing cores, the tensor cores doing the actual multiplying, are incredibly fast. But the memory chips storing the data, the HBM or high bandwidth memory, are relatively slow, and moving data from the memory into the cores requires physical energy and time.
Right.
Arithmetic intensity measures how efficient you are. If you haul a byte of data out of memory and into the core, how many mathematical operations do you perform on it before you have to throw it out and fetch the next byte?
So high arithmetic intensity means you pull a chunk of data into the core and run thousands of calculations on it before going back to the well.
Exactly.
And low arithmetic intensity means you fetch a byte, do one simple addition, and immediately have to wait for the memory to send you another byte.
Exactly. And that dictates the y-axis, which is attainable performance.
Measured in what?
measured in FLOPS, floating point operations per second. This is the actual physical speed limit of the GPU. How fast is the silicon actually crunching numbers in real time?
And the physical shape of this graph gives it the name roofline.
Yes.
It starts at the bottom left with a steep upward slope and then abruptly hits a hard, flat, horizontal plateau at the top. The slope and the roof. What do those two zones represent?
Where your algorithm lands on that shape tells you everything about your architectural efficiency.
Okay.
The sloped part of the graph is the memory-bound region. If your operations have low arithmetic intensity, like the element-wise operations, the normalizations, the O of D times H calculations we discussed earlier, you are trapped on the slope.
Why are you trapped? Like, what is physically happening on the chip in that moment?
On the slope, the GPU's processing cores are effectively starving.
Starving for data.
Yes, they execute the simple math instantly, and then they sit idle, twiddling their thumbs, waiting for the memory bus to deliver the next chunk of data.
That sounds inefficient.
Highly inefficient. Your overall speed isn't dictated by how fast your cores are. It's bottlenecked entirely by the physical width of the copper wires connecting the memory to the processor.
But obviously, if you are renting an H100, you don't want the cores sitting idle. The goal is to climb the slope and hit the roof.
Exactly. And this is where the 6ND formula saves the architecture. High-density operations, the massive O of ND matrix multiplications, push you far to the right on the x-axis.
Oh, because they've reused the data so much.
Right. They have incredibly high arithmetic intensity. Because you are multiplying massive blocks of n parameters against massive blocks of d tokens, you can haul a single chunk of memory into the core and perform thousands upon thousands of m operations on it before needing a fresh delivery of data.
And once your arithmetic intensity gets high enough, you push right off the slope and hit the roof, the compute-bound region.
Right. Once you hit the roof, the dynamic flips. The memory bandwidth is no longer the bottleneck. The cores are fully saturated with data, and they are computing as fast as the laws of physics and silicon will allow.
You're maxed out.
You are extracting the maximum possible value from the hardware. The only way to process faster when you are on the roof is to physically buy a faster, more expensive GPU.
So if I'm an AI lab director staring at a dashboard, monitoring a 10,000 GPU cluster, how do I know if my engineers have successfully written code that sits on the roof, or if they've written inefficient code trapped on the slope?
You track a metric called MFU, Model Flops Utilization.
MFU.
MFU is the brutal reality check. It is the ratio between the theoretical FLOPs your model should be doing, our 6ND formula, and the actual measured output of the graphics cards in real time.
So if I calculate that my training run requires 100 quintillion FLOPs, and my hardware is rated to do 1 quintillion FLOPs per second, it should take 100 seconds.
Right.
But if it actually takes 300 seconds, my MFU is terrible.
Precisely. If your MFU is at 30%, it means your GPU cores are only doing useful math 30% of the time.
And the rest of the time.
The other 70% of the time, they're trapped on the slope, waiting for memory or waiting for data to travel across the network cables connecting the different servers.
Right.
An MFU of 30% means you are literally setting 70% of your cloud budget on fire.
Wow. What is considered the gold standard for MFU in the industry right now, then?
It's incredibly difficult to maintain high efficiency across thousands of chips. If you can push your MFU over 60%, your optimization is considered world-class.
Just 60%.
Yeah, 60% is amazing. You have successfully balanced the memory bandwidth and the compute cores resting firmly on the roofline.
And how do they improve it?
The primary lever engineers pull to achieve this is increasing the batch size.
Which maps directly back to our formula.
Yeah.
Increasing the batch size is increasing the variable D.
Exactly. By feeding a larger block of tokens into the matrix multiplication at once, you artificially increase the arithmetic intensity. You force the cores to do more math on the weights they've already loaded into memory, ensuring they never starve for work.
This is all coming together, bringing all of this theoretical math and hardware physics back to your real world, the listener's world.
Let's do it.
We've explored the first principles. We've traced the 6ND formula down to the individual multiply-accumulate operations. We've seen how it mandates the selfless passing of blame. And we've mapped it onto the physical memory bottlenecks of the roofline model. Let's look at how the industry synthesizes this into the God formulas of AI cost budgeting. How do companies actually project the capital required to build a frontier model?
The entire financial architecture of the AI industry relies on 3 core formulas derived directly from what we've unpacked today.
Okay, 3 formulas.
The first formula is our baseline. 2ND.
Right. 2ND dictates the economics of inference. It is the cost of running the model in production. When a user queries ChatGPT, the model only executes the forward pass. There is no loss function, no backpropagation, no gradient calculation. The locked machines process the messenger, and that's it. 2ND.
The second formula is 6ND. This dictates the economics of total training.
The big one.
This is the upfront capital expenditure required to build the model's intelligence from scratch. It comprises the 10ND forward pass, the 10ND selfish weight updates, and the 10ND selfless activation gradients required to cascade the learning.
Okay, and the third formula. Because 6ND requires us to know what D is, how do engineers decide how many tokens to feed the model in the first place?
The third is a highly influential heuristic discovered by researchers at DeepMind. It's known as the chinchilla optimal ratio.
The chinchilla ratio.
It mathematically models the relationship between model size and data volume. The rule states that D is roughly equal to 20 times N.
So for every single parameter you add to the model, you must apply 20 tokens of training data to train it optimally.
Yes. If you train a massive parameter model on too little data, the model is undertrained, and you've wasted compute on parameters that never reach their potential.
Makes sense.
If you train a small model on too much data, you hit diminishing returns, and you are wasting compute running epochs that yield almost zero intelligence gains. The chinchilla ratio ensures your 6ND budget yields the absolute maximum intelligence per dollar spent.
Let's put these God formulas to the test with a massive real-world application. Let's walk through the hypothetical scaling scenario based on the source text.
Okay, let's run the numbers.
Let's say we are a tech company, and we want to train a model roughly the size of Llama 3. We want a 70 billion parameter model.
Solid size.
That establishes our n variable at 70 times 10 to the ninth. And based on the chinchilla rule, 20 times n, we need a massive data set. Let's push it slightly past chinchilla and say we have 2 trillion tokens of high-quality data.
Okay.
That establishes our d variable at 2 times 10 to the 12.
We have our variables. Now we plug them into the total training formula, 6ND.
Okay, what does that look like?
The total FLOPs required to build this intelligence equals 6, multiplied by 70 billion parameters, multiplied by 2 trillion tokens.
So 6 times 70 times 10 to the ninth times 2 times 10 to the 12th.
Exactly.
If you run that arithmetic, the result is 8.4 times 10 to the 23rd FLOPs.
Yep.
8.4 times 10 to the 23rd power. That is an almost incomprehensible volume of mathematical operations. It's approaching Avogadro's number.
It is a staggering amount of compute. But once you have distilled the ambition of a frontier AI model down to that single massive number, the budgeting becomes a simple exercise in division.
How so?
You take that 8.4 times 10 to the 23rd FLOPs, and you divide it by the actual real-world FLOPS speed of an NVIDIA H100 chip.
And you must factor in the MFU, right?
Yeah.
You can't use the theoretical speed on the box. You have to use the realistic speed you expect to hit on the roofline, say 50 or 60%.
Exactly. Once you divide the total FLOPs by the effective hardware speed, the math tells you exactly how many seconds it will take a single GPU to process the entire training run.
Which would be centuries for one GPU.
Right. And since taking several centuries to train a model is bad for business, you divide that total time by the number of GPUs you intend to string together in a cluster.
Say a 10,000 GPU cluster.
Exactly. And that final division outputs the exact number of days you need to rent the server farm.
Wow.
Which you multiply by the hourly rate of the hardware, and suddenly you know exactly how many tens of millions of dollars you have to wire to the cloud provider before you can even begin.
That is the ultimate power of understanding first principles.
It really is.
You can trace a $100 million data center invoice all the way down to the architecture, past the roofline model, past the selfless activation gradients, down to the simple physical reality that a single parameter needs to execute one multiplication and one addition during a forward pass.
It is an incredible architectural journey.
We started with a seemingly arbitrary formula, 6ND, and cracked it open. We saw that the first 2ND is spent simply making a prediction, the forward pass, the cost of inference.
Then we plunged into the backpropagation phase.
Right.
We accounted for the 10D spent on task A, the selfish compute required to calculate the weight gradients and fix the local tools.
Yep.
And we tracked the final 2ND to task B, the selfless compute burning massive resources simply to calculate an activation gradient, packaging up the blame to send backward down the line.
We analyzed how this specific math is forced into existence by the dual nature of our parameter count, n, where the gradient calculations inevitably sum over both the sequence of time in our data batches and the physical density of space in our network connections.
It all balances out.
And finally, we saw how that dense mathematical load dictates whether our multi-million-dollar GPU clusters are running efficiently on the compute roof or starving for data on the memory slope.
The physical connection from pure, abstract linear algebra to the brutal logistical realities of renting massive clusters of hardware is just profound.
It really is.
It's a testament to how aggressively this fundamental math scales.
So, the next time you see a headline about an AI startup raising $5 billion strictly for compute, you now have the exact blueprint of where that capital is going.
Every dollar.
They aren't buying digital magic. They're funding a network of billions of parameters, running trillions of microscopic blame games, multiplying matrices relentlessly to escape the memory wall.
You now hold the mechanical blueprint of the AI economy.
But before we sign off, I want to leave you with a final provocative thought. Something to consider that challenges the very foundation we just spent an hour building.
Oh, this is a good one.
The entire 6ND God formula, this incredibly elegant symmetry where everything perfectly balances out to chunks of 2ND, relies entirely on a single mathematical prerequisite.
Right.
It only exists because modern models predominantly use dense layers.
Right. Fully connected layers where every single input token is forced to interact with every single output parameter.
Exactly.
That absolute density is what guarantees the math will always scale at O of ND across both time and space.
But what happens to the multi-billion-dollar economics of AI if the architecture abandons dense layers? We are already seeing the rise of sparse architectures like Mixture of Experts, where an input token only activates a tiny, localized fraction of the network's parameters.
Yes, sparsity changes everything.
If an incoming signal only talks to 1% of the machines in the hallway, that beautiful symmetrical O of ND math shatters.
N no longer means total parameters.
Exactly. If the density breaks, the 6ND rule becomes completely obsolete. What does the fundamental cost of intelligence look like then?
It's a great question.
If we are no longer bound by the gravity of 6ND, how do we physically budget for the next generation of artificial intelligence?
That is the exact mathematical frontier that the architects at the absolute cutting edge are desperately trying to map out right now.
We started this journey looking for the absolute precision of a physical blueprint. We found it locked inside the dense matrix math of 6ND. But in technology, blueprints are only permanent until someone figures out how to build without them. It has been incredible unpacking the architecture with you.
It's been a blast.
Thank you for joining us on this deep dive into the true first principles of AI compute. Keep questioning the math, and we will catch you next time.